Dear students, so we are starting with our lecture number 38, that is vibration measuring instruments, that is part 3. So in this lecture we are going to see the remaining vibration measuring instruments. So in last two lecture we have seen the displacement measuring instruments, velocity measuring instruments, and the acceleration measuring instruments. Now today we are going to start with our next instrument, which is called as frequency measuring instruments. So this is our third lecture in unit number 5, that is measurement and control of vibration. So we are starting with our lecture. So first, frequency measuring instruments. So the frequency measuring instruments are the instrument which measures the frequency. So most of frequency measuring instruments are of the mechanical type. These instruments which are used for frequency measurement is of mechanical type, and it is generally based on the principle of resonance. This is generally based on principle of resonance. Now we know that resonance. Now resonance is nothing but when the frequency of external excitation frequency is coincide with the natural frequency of the system, then there will be a resonance occurs, and at that resonance the system or a body is vibrates with maximum amplitude. So that is nothing but the principle of resonance. So these frequency measuring instruments are based on the principle of resonance. So the following instruments are used to measurement of the frequency of any vibrating body. So first instrument, that is frequency measuring instrument, is the single reed frequency meter, which is also called as Fullerton tachometer. So this is the first instrument which is used for measurement of frequency. Second instrument is multi-reed frequency meter, or it is also called as Graham tachometers. And the third instrument which is used for frequency measuring, it is stroboscope. So these are the three instruments which are used. These are the three basic instruments which are used for frequency measuring instruments. So we are starting our first instrument, that is single reed frequency meter, which is also called as Fullerton tachometer. A single reed frequency meter, which is also called as Fullerton tachometer. So this single reed frequency meter or Fullerton tachometer is as shown in this figure. So this is the first figure, which is this figure which is pointed by me. It is a single reed frequency meter. So it consists of a thin strip. So this is your thin strip. So it consists of a thin strip, or it is also called as a reed. So this is called as a strip, or it is also called as a reed. REED, reed, with a mass attached to one of its end. So the mass is attached to this one of its end. The other end of strip is passes over the vibrating body. So at one end of this strip, the mass is attached, which is known to us, and other end, the vibration body is passes over that strip or reed, whose natural frequency is to be measured. The pre length of cantilever of a strip or a reed L can be changed by means of screw mechanism. So this is the L is the length, that is cantilever length of strip or reed can be changed by means of this screw mechanism. So this length can be changed. So by either tightening or untightening of the screw, we can change this length, that is cantilever length. So therefore, at free length, the frequency at each free length of strip or a reeds corresponds to different natural frequency, because we know that the natural frequency Fn is nothing but the square root 1 upon 2 pi square root of g by L. This is another formula. G is your gravitational acceleration and L is your length. So if we change the length, then there will be the change in natural frequency. So the different free length of strip or a reed are calibrated for natural frequency. So there are different natural frequency based on different length of this free end of the cantilever beam or cantilever length. So the screw mechanism is adjusted so that there will be the change in strip or change in length till the amplitude of vibration becomes maximum. Means we have to change this length until there will be a resonance condition occurs. At that instance, at some instant or at that instance, the excitation frequency of vibrating body is equals to the natural frequency of this strip, that is resonance condition occur. When there is maximum amplitude is there, so at that condition there will be the resonance condition occurs. So since the reed are calibrated along the length in terms of its natural frequency, the frequency of vibrating body is read directly on that strip. When there will be a resonance, at that condition we have to measure the frequency at this strip. So this is the first instrument which is used for the single reed frequency meter, or it is also called as Fullerton tachometer. Now the second instrument, it is multi-reed frequency meter, or it is also called as Fram tachometer. So this multi-reed frequency meter, it is shown in this figure. So it consists of the number of strips. In case of single strip or single reed, there is only one strip. But in case of multi-reed frequency meter, there are number of strips or reeds in the form of cantilever. So these are also cantilever from which one end is fixed, carrying a small masses at free ends. So at this free end there is a small mass. So each reed has a different natural frequency. So this reed has different natural frequency, say 1 Hz. This reed has second natural frequency, say 2 Hz, so on. This reed has a different natural frequency. So that there are n number of strips having n number of natural frequency. So each reed has different natural frequency, and accordingly that frequency is marked on that strip or a reed. When this instrument is mounted on any vibrating body whose natural frequency is to be measured, the reed whose natural frequency is nearest to the excitation frequency of the vibrating body vibrates with maximum amplitude. For example, if this reed vibrates with maximum amplitude, if we vibrates with maximum amplitude, then we can say that this is the natural frequency of that vibrating body. So the reed or strip which vibrates maximally or which vibrates with maximum amplitude, because of there will be the resonance, because this natural frequency of strip is equals to the frequency of vibrating body. So if that resonance condition occur, then this the strip which is vibrating maximally, the frequency, the natural frequency can be found out from the frequency of vibrating reed. So this is the second instrument, which is multi-reed frequency meter, which is also called as Fram's tachometer. So these are the two instruments. Now next, so next instrument is your stroboscope. So this stroboscope is an instrument which produces light pulses. This stroboscope is instrument. This is the control panel of stroboscope, and this is the light pulse which produces. It is a pulsating lamp which produces the light pulse, and the frequency, that is natural frequency of this pulse light, it is shown in this control panel in the digital form. So this is the stroboscope. So what is stroboscope? Stroboscope, it is an instrument which produces light pulses at equal interval of time, which can be varied. So that light pulse which produces at equal interval of time, which can be varied. So the frequency of light pulse which are produced can be changed and easily read from control panel. So from this control panel, you can read the frequency. For example, there is 49.18 is the frequency. So that can be viewed from this control panel. When reference point on a vibrating body is viewed with pulsating light which is generated by stroboscope, it will appear stationary. When frequency of pulsating light is equals to the frequency of vibrating body, therefore the frequency of vibrating body is read from control panel, that is directly read from control panel. So when reference point on a vibrating body is viewed from pulsating light which is generated by stroboscope, it will appear to a stationary when frequency of, so that light becomes stationary. So that light appears stationary or becomes stationary when this condition is happened. That is, frequency of pulsating light is equals to frequency of the vibrating body or a system. And when that pulse light is stationary, we have to read the frequency from that control panel. Now, the advantages of this stroboscope is that it does not have any contact with vibrating body, because there is generating a light and there is no contact between the vibrating instruments and the body or a system whose vibration is to be measured or frequency is to be measured. So hence it is non-contact type frequency measuring instruments. So this is the advantages of this stroboscope. The lowest frequency up to 15 Hertz can be measured easily with the help of this stroboscope. So this is the these are the three instruments which are used for measurement of frequency. Now next, we are going to start with the next important point, which is known as vibration exciters, So vibration exciters, it is also called as vibration shakers. Vibration exciters, it is also called as vibration shakers. So these vibration exciters or shakers are used to produce the required cyclic excitation force at required frequency. So these vibration exciters or vibration shakers are used to produce required cyclic excitation force at a required frequency. This cyclic excitation force produced by an exciter can be applied to a machine or structure. Can be applied to a machine or a structure so as to study the dynamic characteristics. So as to study the dynamic characteristics. So generally, there are various types of exciters which are used in case of these vibration exciters. So that exciters are mechanical exciters, then electromagnetic exciters, and the electrodynamic or hydraulic type of exciters. So we are starting our first exciters, which is called as a mechanical exciters. So I will show figures of these mechanical exciters. So these are the mechanical exciters. So this is first mechanical exciters, and this is another mechanical exciters. Now in mechanical exciters, these are excited by using two mechanisms. So first, by using Scotch-Yoke mechanism. So this is the diagram which is shown for Scotch-Yoke mechanism. So this is a mass which having displacement at any time t is equals to r sine of omega t, and the force which is produced by this exciter, it is given by F is equals to m omega square r sine of omega t. So this is any vibratory structure. So in that diagram, there is an automobile or car, which is a vibrating structure or a vibrating body. Above that, there is a Scotch-Yoke mechanism, which consists of a crank. So this is the crank. When this crank is rotating, so there will be the movement of this mass through this guide in vertically upward or downward direction, depending upon the rotation of that crank. So we can say that in the Scotch-Yoke mechanism or in mechanical exciter, the Scotch-Yoke mechanism can be used to produce harmonic vibrations, or we can say they are used to produce harmonic excitation force, which is shown in figure. So in this system, there is a crank driven. So in this system, the crank of mechanism is driven with constant speed, or we can say variable speed, by means of motor. So this crank, it can be moved in constant speed or it can be moved in variable speed by means of motor. The other end of crank, which is slide into this slotted rod, which reciprocates in this vertical drive. So this is a vertical guide. So that rod is reciprocating through its vertical drive. So the harmonic force that can be applied on a structure by these exciters, that is Scotch-Yoke mechanism type of mechanical exciter, to which exciter is attached, is given by F is equals to m omega square r sine of omega, where m is the mass of this mass attached to this Scotch-Yoke mechanism in kg. Then omega is the crank speed in radian per second. Then r is your the radius of crank in meter. So this is the first. Now this type of Scotch-Yoke mechanism is used in case of mechanical exciters. Now there is another example of this mechanical exciter, that is this two rotating masses are there. So this is first rotating mass and this is another rotating mass. So there are two rotating masses. There is a structure, and on that structure there are two rotating masses are attached. Now this is your any vibrating structure. Now in this case, it is a building frame. It is an vibrating structure. Now there is an girder of this building frame upon which there are two rotating masses. So one mass is rotating in clockwise direction, another mass is rotating in anti-clockwise direction. So single mass produces a force which is equals to F is equals to m omega square r sine of omega. So two masses will produce the force, that is F of t is equals to 2m r omega square. Now there is a cos of omega because this is a vertical force. Now these are the horizontal force. So, sorry, these are the vertical force because the angle is with vertical. So that is 2m r omega square cos of omega t. So the harmonic force can also be created by means of two masses rotating at same speed but in opposite direction, as shown in this figure. When two masses of equal magnitude rotate at an angular velocity omega and radius r, that is capital R is the radius, then vertical sinusoidal force which is produced, it is given by 2m r omega 2m omega square r sine of omega t, and this is horizontal force. So vertical force is 2m r omega square sine of omega t. It is not a cos omega t, it is sine of omega t. Where m is the horizontal rotating unbalanced mass, omega is Planck's speed, and capital R is the radius of crank. So the horizontal components of two unbalanced force act opposite to each other. Hence, the resultant horizontal force will be zero. So only there will be a vertical force. So horizontal force becomes zero. So the cos term is becomes zero. So only 2m r omega square sine of omega t. So this is the term in case of this second, that is mechanical exciter, second type of mechanical exciter, that is the force which is produced by two rotating masses. Now, this type of mechanical exciters or shakers can be used to generate a relatively large load. These are used to generate a relatively large load between 250 to 25,000 Newton. This type of exciters, that is rotating, when two masses are rotating. So this type of exciter, so this second type of exciters which produces the force which is ranging from 250 Newton to 25,000 Newton. And this first type, that is Kirchhoff mechanism type of mechanical vibration, which are used to generate the load which is less than 700 Newton. Which is less than 700. So for medium excitation, which is less than 700 Newton, we can use this. And for more than, we have to use this type of mechanical exciters. Now next, we are going to see the next exciter, which is called as the electrodynamic exciters. Electrodynamic exciter. So the schematic diagram for this electrodynamic exciter or shakers are also known as the electromagnetic exciters. So which is shown in this figure. So it consists of, so electrodynamic shaker, it can be considered as, or we can say electrodynamic exciters can be considered as the reverse of electrodynamic transducer. It can be considered as reverse of electrodynamic transducer. So when the current is passes through the coil, when the current is passes through the coil placed in magnetic field. So this is the coil which is placed in this magnetic field. So when there is a current which is passing through that coil, which is placed in magnetic field, a force F, that is the force F, which is proportional to the current I and magnetic flux density D, is produced, which accelerate or which produce a force or accelerate the component which is placed on shaker table. So for example, this is a table or exciter table, and on that exciter table some component will be placed. So because of this coil, there is a magnetic coil, and when we passing through a current through this magnetic coil, and this is a magnet, so because of that there will be the magnetic flux or field which is produced, and because of this magnetic field there will be the force which is generated, which is proportional to the I and flux density of this magnet. So this force which is produced by means of this electrodynamic shakers or a vibrator or exciter, it is given by F is equals to BIL, where, sorry, DIL, DIL. So D is your the magnetic flux density, I is your current, and L is the length of the coil. So the magnetic field which is produced by permanent magnet in the small shakers, while an electromagnetic is used for large shaker. So for small shakers, that is for small electrodynamic shakers, we used a magnetic field which is produced by permanent magnet. But for large shakers, we have to use an electromagnet. The magnitude of this acceleration, that is acceleration of table, the magnitude of this acceleration of table is depends on the maximum current, that is I, and the masses of component, and the moving element in the shakers. So it is depends on, that is I, that is current flowing through this coil. Then it is depends on the masses of the components. So exciting cable, flexible support. So all these masses. So this mass M, and it is depends on the third component, which is moving element of the shakers. So the mass of this moving element. If the current flowing through this coil varies harmonically with time, if current flowing through the coil varies harmonically with time, the force produced also varies harmonically. Harmonically means sinusoidally. When current flowing through the coil varies harmonically with time, then the force which is produced by this exciter is also varies with harmonically. On the other hand, if direct current is used to energize coil, then there will be a constant excitation force which is generated. There is constant excitation. So we can generate either harmonic excitation or we can generate a constant excitation. If we use a constant current through the coil, we get constant harmonic force, and if we varies the current with time harmonically, then we can get a harmonic excitation force. So the electrodynamic exciter can be used in conjunction with inertia and spring to vibrate a structure. So this type of exciter, it is used in conjunction with inertia and spring to vibrate the structure, since the coil and moving element have linear motion. The coil and moving element have linear motion. They are suspended from flexible support. They are suspended from flexible support as shown in this figure. So thus electrodynamic exciter has two natural frequency. So it has two natural frequency. So one corresponds to natural frequency of flexible support. So there are two types of natural frequency. So one natural frequency corresponds to the flexible support, and other corresponds to the natural frequency of moving element. So there are two natural frequencies which can be made large. So the two resonance frequency as shown in this figure, that is natural frequency of first flexible support and second natural frequency of this moving element. The operating frequency range excitation is lies between these two resonance frequency. So this is the first resonance frequency and this is second resonance frequency. So the operating range of that natural frequency, it is lies between this frequency range and this frequency range. So this is constant acceleration. So this is the operating range of natural frequency. So the electrodynamic exciters are used to generate a force of 30,000 Newton. So this type of film, if we see the mechanical exciter, that is Kochuk mechanism, it is used to excite, or which is used to generate a force of 700 up to 700 Newton. The two rotating masses are used to generate the force of 250 to 25,000 Newton. But this type of electrodynamic exciters are used to generate the force which is up to 30,000 Newton, and the displacement of this moving element or this flexible support, it is up to 25 mm, and the frequency we can produce by means of this electrodynamic exciter is 5 Hz to 20 kilohertz. So in today's lecture, we have seen some frequency measuring instruments, that is single reed frequency meter, then multi reed frequency meter, and stroboscope. And also in today's lecture, we have seen the vibration exciters or vibration shakers. So there are basic two type of exciters. So first one is mechanical exciter. In that there is two mechanism can be used. One is Kochuk mechanism and another is two rotating masses, that is unbalance of two rotating masses. And we have seen the electrodynamic exciter or shakers. So thank you very much.